Welcome to The Explainer. Today, we're stepping into a high-stakes, honestly pretty invisible world that's hiding right beneath the hood of your car. It's the world of engine oil formulation. Now, you might think engine oil is just a simple maintenance item, right? A routine fluid swap you do maybe once a year just to keep things running smoothly. But as we'll see today, modern engine oil is actually at the very center of this massive multi-billion-dollar tug-of-war. It's a battle between strict global emissions regulations, theoretical fuel efficiency, and the actual physical survival of your car's engine. We're going to explore some highly surprising, frankly shocking trade-offs that car manufacturers are making right now.
Okay, let's dive into this. 95 euros. Now, I know it kind of seems like a small number at first glance, but it represents a massive financial hurdle for modern automakers. Under really strict European Union regulations, car manufacturers are required to hit a fleet-wide average emission target of 95 grams of CO2 per kilometer. But here's the catch. For every single vehicle sold, the manufacturer pays a penalty of 95 euros for every single gram per kilometer that they exceed that target. So you multiply that by millions of cars sold, and you're looking at absolutely staggering financial penalties. This immense regulatory pressure has forced automakers into an intense pursuit of better fuel efficiency, optimizing their fleets by literally any means necessary.
And to really understand how they're solving this, we kind of have to follow the money, because there is a fundamental financial asymmetry in modern engine design. By optimizing a car to save just a tiny bit of fuel over its entire lifetime, the consumer might save, around 100 euros at the pump. But to get that 100 euro saving, the engine is subjected to conditions that dramatically increase the risk of premature engine failure. And that's a catastrophic event that can easily cost the consumer 1,000 euros or more to repair. So the manufacturer completely avoids millions in regulatory fines, but you, the driver, take on all the financial risk. So how exactly are they doing this? Well, let's look at the engineering.
Which brings us to Section 1, Fighting the Friction Enemy. To avoid those steep regulatory penalties we just talked about, automotive engineers are targeting an invisible enemy hiding deep inside the powertrain: mechanical friction. And this brilliantly illustrates the battlefield. Notice the friction torque loss mapped out here for a typical 1.6-liter gasoline direct injection engine. The data shows us that friction literally eats up around 1/10 of the useful torque the engine can actually produce. It's just wasted energy. To hit those strict CO2 targets, engineers absolutely have to claw back that lost energy. Now, at higher engine speeds, the prevailing friction is hydrodynamic, meaning it's caused by the engine parts fighting through the thickness or the viscosity of the engine oil itself. So what did the industry do? They came up with the thin oil solution. For decades, passenger cars ran on thick, viscous oils. Think of your classic 15W40. But recently, there has been this massive shift toward ultra-thin oils. First, it was 0W-20, which brought a 3 to 4% improvement in fuel economy. But now, the industry is migrating to incredibly thin liquids like SAE-0W-8. By dropping the viscosity to these extreme levels, engineers can squeeze out an additional 2 to 3% improvement in fuel economy, simply because the engine components no longer have to push through thick oil. It flows almost like water. It sounds like a perfect, elegant solution to pass those emissions tests, right? Well, this brings us to Section 2, the formulator's dilemma. Because, as we know, physics always demands a trade-off, and this is exactly where the plot twist happens. We're looking at a very delicate, highly dangerous balancing act between achieving the theoretical fuel efficiency required by law and actually maintaining the protective barrier that keeps an engine from destroying itself. Which naturally leads us to a pretty vital question. So what happens when oil gets too thin? We know it reduces fluid drag at high speeds, sure. But an engine isn't just a simple pump. It's a highly complex machine with heavy metal parts sliding violently against one another under extreme heat and pressure. Now, what's really interesting about this slide is how the visual data answers that exact question. Tracking power loss across different engine components reveals a total paradox. Notice what happens when we drop down to that ultra-thin 0W-8 oil. The bearing friction goes down, that's the blue area, but look at the piston assembly and valve train. Paradoxically, the overall power loss there actually spikes back up. Why? Because the oil is now so incredibly thin that it utterly fails to maintain hydrodynamic film. That crucial liquid barrier between the metal parts just collapses, and you get pure metal-on-metal boundary friction. The engine literally works harder just to scrape its own parts together. And that friction isn't just a harmless loss of efficiency. It leads us perfectly into Section 3, the real cost of wear. Because we really must shift our focus from theoretical power loss to the very real, very destructive physical damage happening inside engines that simply were not designed to handle these ultra-thin fluids. Let's look at the actual maps from simulated engine health tests to really put this into perspective. You can see fuel economy gains mapped out in green. And sure, there are efficiency benefits when you rev the engine at neutral or under low loads. But look at the mapping on the far right. That massive dark red danger area, that indicates degraded fuel economy and a severe, severe drop in bearing health. And the scary part is, this red zone occurs at low RPM and high engine loads, which is exactly the condition you experience when you're accelerating from a stoplight or pulling a heavy load. In this specific high-load, low-speed red zone, the protective hydrodynamic film of a 0W-8 oil completely collapses. It just exposes the engine internals to severe risk. Let's move to and see how this builds into actual real-world consequences. This theoretical damage becomes glaringly obvious when we look at actual physical wear measurements. Using highly advanced radioactive tracer testing to detect microscopic metal wear, researchers ran a gasoline direct injection engine through various everyday driving conditions. Now, the blue bars represent a standard, thicker 5W30 oil. The red bars, that's a thinner 0W-16 oil. Across roughly 2/3 of the testing conditions, things like transient loads, high speeds, trailer towing, stop-and-go traffic, the thin oil resulted in these massive, staggering red spikes of metal wear. The blue bars clearly show that the thicker 5W30 oil kept the wear rates incredibly low and safe. Simply put, the thinner the oil, the faster the engine eats itself. Which brings us right back to that ultimate asymmetry we touched on earlier. The car manufacturer formulates these ultra-thin oils to save maybe 1 to 2% on fuel during standardized testing, right? And that drastically reduces the millions of euros they'd otherwise pay in emission fines. But the consumer? You're the one who inherits a vehicle where the internal components are grinding away at an accelerated rate. You take on the severe financial risk of a premature engine death. Now, if you think transitioning to hybrids solves this whole mess, you'd unfortunately be mistaken. Which brings us to Section 4, the Hybrid Powertrain Challenge. The massive rise of hybrid vehicles actually adds a completely new and, honestly, bizarre layer of complexity to this entire science of wear and lubrication. Because hybrid internal combustion engines do not run continuously, they often fail to reach their optimal working temperature, and this creates a deeply visceral, kind of gross reality. At low temperatures, water condensation forms on the engine cylinder walls. This water eventually drips down and mixes directly with the engine oil in the crankcase. As researchers explicitly noted in the source material, in extreme cases, this mixture causes the oil to emulsify and turn into a mayonnaise-like substance. As you can probably imagine, an engine trying to lubricate its heavy metal parts with cold mayonnaise is going to suffer from catastrophic friction and wear. To combat this, hybrid engine lubrication comes with entirely new hurdles. Because the internal combustion engine frequently stops and starts, the protective oil film we talked about earlier is constantly collapsing. Therefore, hybrid oils can't just rely on viscosity alone anymore. They depend incredibly heavily on aggressive chemical friction modifiers and extreme anti-wear additives. Formulators are literally using complex chemistry to forcefully coat the metal parts, desperately trying to prevent them from welding together during those cold, unlubricated startups. So the crucial point is really one of perspective. When we zoom out and look at the whole life cycle analysis, we absolutely have to talk about embodied CO2. Every single new vehicle manufactured arrives on the planet with about 10 tons of CO2 equivalent emissions already generated. That's just from making the steel, forming the plastics, and physically assembling the car. That manufacturing footprint represents 20 to 30% of the vehicle's entire lifetime emissions before it even drives its first mile. Which leaves us with this genuinely provocative thought to impartially consider based on all this data. If saving a few drops of fuel destroys the engine prematurely, are we really saving the planet? By mandating ultra-thin engine oils just to reduce fuel emissions by a tiny couple of percentage points on paper, we are measurably increasing engine wear. If an engine fails prematurely and the entire vehicle has to be scrapped and replaced years earlier than it normally would be, the heavy manufacturing carbon footprint of building a replacement vehicle entirely erases the tiny amount of fuel saved. Are we actually helping the climate, or is the strict pursuit of tailpipe emissions inadvertently doing way more harm to the environment as a whole? It's a fascinating dilemma, and it's one the automotive world is quietly struggling with right now. Thank you so much for joining us for this explainer, and definitely keep questioning what's going on under the hood.